All right, welcome back, everyone. We're still in the lecture on perfect secrecy, and I would say let's start off where we left last time. Do we have any questions? For what we did in the last lecture? No, then let's continue. Okay, so last time we left off with the construction of the so-called one-time pad, right? So how do we generate keys? How do we encrypt and how do we decrypt with a one-time pad? Let's just recall. Let's say our keys, our messages, and our ciphertext, they are all bit strings of length n. To generate a key, we just choose a random bit string of length n. To encrypt a message m, we take this message and XOR and bitwise XOR the key k onto it. And to decrypt, we take a ciphertext and a secret key k, and we also just XOR this key k onto the ciphertext. And we've seen last time that since XORing with any value, doesn't have to be random, with any value is an involution, means k XOR k is just the all zero string, and the all zero string XORed onto a message m is just the message m. This gives us correctness for the one-time pad. Okay. Good, but now for the actually interesting question, namely secrecy. How do we show perfect secrecy of the one-time pad? Well, this is going to be the very first example of a security proof that we're going to see in this lecture. We're going to do quite a few of those. So this very first time, let's do all the steps in great detail. So what is our goal? Well, we want to show that, show that for any distribution, let's call it M of messages, right? And M is now just any random variable supported on the message space, right? Message space was just bit strings from 0 to 1, and M is now just a random variable which generates some distribution of messages. And a uniformly chosen key k, chosen from 0, 1 to the n, that m and here enc k comma m are independent. Right, so that's our goal. And how do we do this? Well, first, let's say M is any message distribution. So we're gonna fix a message distribution M, right? Or whenever we say for any, then for concreteness, we think that this is fixed to something, right? So this is not variable anymore. And what we want to show in the end is that show for all messages, let's say lowercase m in the message space. This is now calligraphy m is now the message space, and all cipher texts C in ciphertext space, it holds that let me just check if I have still space. I do. Okay, it holds that probability of M equals M conditioned on enc K comma M equals C is the same as probability M equals M, right? This was our definition of perfect secrecy. The posterior probability after we've seen the ciphertext C, the encryption of M is the same as the prior probability of just guessing M without ever seeing a ciphertext, right? So again, what this security notion encapsulates, and that's sort of the part of all of this that we kind of have to inhale and get familiar with. What do these equations mean, right? What do these equations try to model? And what this equation or this notion says is that if a message M is chosen from a let's say a distribution M that you know, then seeing an encryption of such a message will not help you in guessing what the message is, right? So guessing before seeing a ciphertext and after seeing the ciphertext are the same. Okay, good. And how do we do this? Well, we want to compute this guy here. How would we start when we're given a conditional probability? What's would be a natural thing, or first thing to try to do when we so we're having a conditional probability on the left side. And let me take, do I have a pointer here? I think, no, I don't have a pointer. Let's see. Do I have a pointer? No, I don't get a pointer. Too bad. So we have this, let me just underline it again. We have a conditional probability, and the thing on the left side is rather easy, but the thing on the right side is rather complex. What could we try to do to compute this conditional probability? Any guesses? Yes, please. Bayes rule. Let's try Bayes. Exactly. So, let's maybe go to the next. To the next page to declutter a little bit. Let's do Bayes. Whoops. So, probability of M equals M, given that enc K comma M equals C, is the same as probability enc K comma M equals C, given M equals M, times probability M equals M divided by probability enc K comma M equals C. Okay, good. What can we do now? Now we we have three additional probabilities floating around. Let's maybe start with this probability here. Can we simplify something here? So we have some weird and complex distribution, capital M, but I'm going to tell you that what this distribution does now doesn't matter because it outputs a fixed message lowercase m. So what's this probability now? If we condition that some weird distribution outputs a fixed message. What can we do with the M on the left side here? What does this event become if we condition on M equals M? There we go. So this is now probability enc k lowercase m equals C. Do we still have to condition on capital M equals M? You can tell me. Maybe you have, maybe you have a go.
I think that it might be possible that we replace the whole statement with probability one.
No, let's go slowly. So in this probability here, the one that I'm writing in green, do I still have to condition on capital M equals M? Remember, I told you the key, yes, please. Since the left part is now independent of M, right? Remember, if two random variables X and Y are independent, then probability X given Y is the same as probability X, right? K, the only random choice left on this side here is K, but we know that K is independent of M, so we can drop this conditioning. Whew, good. Okay, so that simplified things a bit, right? I guess most of you should agree with me, but now let's go a step further. We're not talking about any generic encryption algorithm. Two slides earlier, I've given you the definition of what encryption does, right? So encryption of K and M, this is just probability of Kx or M equals C. Okay, I've just plugged in the definition for my encryption. Now let's do a tiny little bit algebra. What I'm gonna do is I'm gonna, in this equation, Kx or M equals C, I'm just gonna XOR M on both sides. And then this is the same as probability K equals C XOR M, right? These two events, K XOR M equals C and K equals C XOR M, they're the same. Because I've just done a tiny little algebraic transformation, XORing M on both sides. That's an invertible function. So those two events are the same. Good. Now, this complex conditional probability that we started with, it shrunk down to something very simple. Can someone tell me what that is? Probability that K is C XOR M. C is anything but fixed, something fixed, and M is something but fixed. Let's also monitor the chat. If someone on the chat wants to say it. So what's this? Yes, please. It's what? What did you say? A little bit louder. One. You said it's one. Okay. Maybe next one. Yes, please. Good. Why? So the answer is it's 2 to the minus n. Yes, please.
Because we have, I mean, the C is something like, could be anything.
So how big is the key space?
2 to the power of n, and they have uniformity.
There we go. That's the answer. That's the answer. Right? K is uniformly a uniformly random key, and the number of keys that we get are 2 to the n many. So it's 1 over 2 to the n, or 2 to the minus n. Woo, okay, that was good. So next probability. Let's look at this guy down here. Ooh, what could we do with what could we do with, yeah, with this probability?
We could use this calculate operator export, and then we could see that this is a bijection, and then we see that this also doesn't change anything, so it's the same as before.
Yes, but good. Let's maybe take a mental leap backwards. Remember, I told you about how we were using, let's go back to our example from last lecture where I said this. We have this disease test, right? Where we know this, and that. What kind of tool did we throw at? Yes. Law of total probability. Let's try this, right? So probability of enc k comma m equals c, right? Now m is some stupid random variable, but well, let's partition the entire. Let's get rid of this random variable m just by a capital M, just by conditioning on all possible outcomes, right? So let's go over all messages. Let's call them M prime in 0, 1 to the n, right? And by the law of total probability, by the way, let me write up here, this is just base, so that when you read this later, you're not gonna forget this. So by the law of total probability, this is over probability enc k comma m equals c, condition on capital M equals lowercase m times probability m equals lowercase m. Okay. So what can we do now? So now, again, my capital M was some complex distribution, and in a way, what I'm doing now with the law of total probability is I'm doing a case analysis. Right? I don't know what this M does, but I'm just going through all possible cases of what M could output. Well, if we look at this guy here, what can we do with him? Yes? We already did it above there, right? So this is the same calculation as this, right? So this is probability. Sorry, not probability. This is already directly 2 to the minus n. 2 to the minus n. Okay, let's simplify things a bit. So we have 2 to the minus n times sum m prime in 0, 1 to the n, probability m equals m prime. And what's that? Yes? Thank you. So I repeat for the online audience, this is just 1 because we are summing over all potential outputs of this random variable m, right? So this is 1. So this is just 2 to the minus n. So going back to the above, to the red one, we have now that probability m equals m, given that enc k comma m equals c is just, well, 2 to the minus n divided by 2 to the minus n times probability m equals m. And now the 2 to the minus n just cancels out. And we have, this is probability m equals m. Okay? And I would say we're done, because that's what we wanted to show. The posterior probability is the same as the prior probability. So seeing seeing an encryption of a message M does not help you guessing M, no matter how hard or how easy it is to guess M, right? And here we've seen something that we're gonna see a lot in this lecture. We didn't know what this distribution capital M actually does. This is, as we would say, or as we like to say, not just in crypto, also in complexity theory, this is an adversarial distribution, a worst case distribution, a worst possible distribution. We don't know what it does, but we could still deal with it, right? So because the calculations that we did here were essentially agnostic of what M does, right? Just by using Bayes' law and the law of total probability, we've made this analysis essentially agnostic of the actual distribution of M, right? So we've shown that this analysis here works for any distribution, capital M, and therefore also for the, we could think of it as the worst possible. So we're happy. Any questions? Well, this was our first security proof, only like 20 or 30 maybe to go over the, maybe a few more over the course of this lecture. Are there any questions? Yes, please. The first one here, this one, going removing the conditioning, or so how we went from here to there. How I got rid of the conditioning. Ah, good. So M is any message distribution. However, I asked for M to be independent, or for the key K to be independent of M, right? We have to assume that the key K is chosen independently, right? So here, if we go, please, everyone, do it like your colleague. If you have trouble with a step, please ask. So here, this holds because M and K are independent, right? If you have two independent random variables, let's leave it in this color here. Let's say X comma Y independent, then it holds that probability X equals X condition Y equals Y is just probability X equals X. Okay, that's what we used here. That message and the message distribution and the key are independent. You're having a...
the message and the key, or the message?
No, the message and the key. Just, I mean, to compute the encryption, we need to use the key, right? But to sample a key, we don't need the message. And to sample the message, we're not allowed to use the key, right? So the message distribution cannot depend on the key. Otherwise, we would get something that's called key-dependent message security, which is way out of scope of this lecture, right? This is a rather advanced concept in mostly in public key encryption in modern research. I mean, this has been studied like for the last 20 years now. So well, I mean, more than 50 years after this, right? Key-dependent message security out of scope here, right? So we assume the message distribution doesn't depend on the key. Okay, good. Before I talk, let's move me back into this corner. So why is this simple encryption scheme called the one-time pad? Now, a little bit history again. It was invented by a French man called Vernon in 1917, right? So we're like, wait, aren't we doing like a work from 1949? but yeah, before 1949, we didn't really have a good idea why this scheme is actually secure, right? Because we didn't have a notion of what it means to be secure until Shannon came with this idea of perfect secrecy, where we're asking that the message and ciphertext are independent. Good. So the cipher actually predates the security analysis. But if we look at this scheme, right? So this proof that we have, and this is sort of a little bit hidden in our formalism right now, this only holds if the key is used at most once. If you, let's say, reuse the key, if you condition on several different ciphertexts, then this doesn't hold anymore, right? This holds only as long as you condition on one single ciphertext. Good. And how to overcome this, or how to better model this, will be an issue of today's lecture. But if in this cipher we're reusing the key to encrypt many different messages, then we're essentially implementing the Vigenère cipher on bits, right? So when we compute an XOR of two values, this is just an addition modulo 2. We've seen the Vigenère cipher, that was an addition modulo 26, right? This doesn't take a great deal of abstraction to go from addition modulo 26 to addition modulo 2. Addition modulo 2 is better for computers, of course, right? Because it just fits so well with their binary logic. So if we reuse the key, we get Vigenère, and we know Vigenère is insecure, right? So there's no hope in proving that the one-time pad would still be secure, would still meet this notion of perfect secrecy if we were to reuse the key. Okay, because then it becomes Vigenère, and we know Vigenère is insecure. Let's maybe add this. No hope to reuse key as Vigenère is insecure. Okay, but what that means is if we can use every key only once, oh, this consumes a lot of key material, right? If I want to exchange 1 million bits securely with any of you, we'll first have to establish a key, right? Like we have to meet in person and generate a key. Then we can move apart and we can still send secure messages. But there is now an overhead involved in generating key material, because key material cannot be reused. If you reuse the key, the thing becomes Vigenère and therefore insecure, right? And a question of the next lectures will be, can we do better? Can we get perfect, or let's hope maybe still of today's lecture, can we hope to get perfect secrecy with less key material, right? This could just be an artifact of the one-time pad, that it uses up so much key material. Maybe there are perfectly secret encryption schemes that use shorter keys that are shorter than the messages we want to encrypt, right? Good. Now, we've seen this definition 1, which nicely captures our intuition of what it means for a, what it should mean for a scheme to be secure. But it turns out, and here maybe you have to believe me, this notion is not really easy to work with when we're designing larger protocols. It's a little bit unwieldy, so to speak. And also, more important for us, right? We're still in 1949 and we want to make progress towards the present. This security notion doesn't immediately generalize to weaker security notions. As it turns out, perfect secrecy is an overkill, right? That's, I mean, the biggest possible hammer in terms of security. And as we will see in this lecture, weaker forms of security are, for all practical purposes, good enough, right? A perfectly secure scheme is provably unbreakable. Maybe we're interested in just practically unbreakable schemes, right? But formalizing that, again, is a few lectures or at least one lecture ahead. So this definition that we've seen doesn't generalize to weaker notions. And a first thing that we're going to look into now is we're going to try to find alternative definitions for perfect secrecy, right? Right now we had, I mean, I foreshadowingly called this definition 1. Let's look into other definitions, right? So in the context of historic ciphers, we've seen these so-called distinguishing attacks. The adversary knows that the ciphertext encrypts 1 out of 2 messages, and all he wants to know is, does it encrypt a yes or a no, right? Let's see, maybe this will be good enough, right? In this, as I just said, in this setting, the adversary knows that a ciphertext encrypts 1 out of 2 messages and has to find out which one. So what I'm asking now is this maybe already a minimal attack goal, right? And this leads us to our second attempt at defining perfect secrecy. First one was with conditional probabilities. Now we're saying the following. Let's say in this definition 2, an encryption scheme, keygen EncDec, is perfectly secret if it holds for all pairs of messages M and M prime in the message space, and all ciphertext C, that if you take the message M and encrypt it with a randomly chosen key, then the probability that you get this fixed ciphertext C, right? Now M, M prime, and C are fixed values. Now the probability that when we're encrypting M to get C, we're asking that this is the same as the probability of getting C when you encrypt M prime, right? Where again, of course, the key K is chosen by the key generator. What makes this definition here somewhat nicer than the first one? What was sort of an annoying aspect? Yes, please. No conditional probabilities. Yes, that's one thing. But what I would maybe find most annoying about the first definition was this distribution of messages M, right? There we had to go over all possible message distributions. And this new definition, this new and maybe better definition of perfect secrecy just talks about pairs of messages, right? Instead of talking about any conceivable message distribution, it talks about pairs of messages, right? This definition captures the idea that this definition essentially says, that encryption scheme is secure against any distinguishing attack. Secure or withstands, let's say, withstands any distinguishing attack. right? Now, of course, the question is, if you're secure against distinguishing attacks, are you maybe already secure against any attacks, or are there separating examples, schemes that are secure against distinguishing attacks, but insecure against arbitrary attacks? So that even though you're secure against a distinguishing attack, maybe you can still learn something from the ciphertext about the encrypted message. All right, so let's continue discussing. So these two definitions that we've seen now, well, they were only really concerned with distributions of messages and ciphertexts. But if you remember in the earlier in the first lecture, I've always said, here's Alice, there's Bob, and now there's the adversary Eve, right? So the adversary Eve is not really yet an actor in these definitions. There's not even an explicit mention of an adversary. We just have a few, let's say, probabilistic properties that such an encryption scheme should fulfill, but there's really, I mean, a leap of interpretation necessary to get from these equations to the interpretation why the underlying scheme should be secure, right? So now what I'm really looking for now is a definition which has, let's say, the correct interpretation, or the interpretation that we want the reader to take there, baked into it. Right, and looking ahead in the next lectures, we want to study notions of security where the adversary only has limited resources. Making it shortly, the adversary has to be an efficient algorithm, cannot have unlimited runtime, right? It should be an efficient algorithm. But that's looking ahead. Such an aspect hasn't been captured in the first two definitions. So what we're going to do now with a third attempt at defining perfect secrecy is making this adversary explicit, right? And our starting point now will be, let's say, the second definition, right? In the second definition, we had messages M0, M and M prime, and we asked that they should have the same the encryptions of these messages should have the same distribution. So let's go one step further. Again, let's say keygen encdec is an encryption scheme, and now let's say A is a possibly unbounded and possibly randomized algorithm, and we call this guy mathcal A the adversary. And now we consider the following experiment, right? And here we're going to see a blueprint for all future security definitions where we're defining security of some scheme via an experiment or a thought experiment, if you want so. So here's my adversary. I like to draw him as a box. And now there's a second machine, let's call it the challenger, or the experiment, who tries to see if this adversary can really break my encryption scheme. Okay, so the challenger, you can think of this as a tester. Let's say someone claims I have an algorithm that breaks the one-time pad, and then you're like, yeah, but how do I test this? And well, this definition will tell you now how you can test such an algorithm, right? If someone comes and claims I'm breaking the one-time pad, we have just finishing up this slide, and then we do our break. Then here's an efficient test, right? What does my challenger do? Now, first, the adversary tells my challenger two messages M0 and M1. So I'm allowing the adversary to choose these two messages. Next, the challenger generates a key K using the keygen algorithm. He chooses a random bit B, and now he encrypts MB. Okay, so generate a key, choose a random bit B, and now encrypt one of these two messages, M0 and M1, well, MB, where B is a randomly chosen bit. And we're gonna give C star this ciphertext or challenge ciphertext, call this challenge ciphertext to the adversary, right? And now I'm asking the adversary to make a guess for this bit B. Okay, and his guess, we call it B prime. And we say the adversary wins if his guess is correct, and he loses if it's false. If you were an adversary, what kind of a strategy to guess this bit could you do? Yes? Choose randomly. Then what's your success probability? 1/2, exactly. So we know that just by implementing the most stupid strategy of choosing B prime random, we're already getting a success probability of 1/2, right? So that's sort of the baseline we're gonna compare now to. And we call this a ciphertext indistinguishability experiment. And let's call the output, right? What this thing outputs in the A. And just to wrap that up, now we have definition 3. An encryption scheme keygen EncDec is perfectly secret if it holds for every adversary A, for every conceivable attack, that the probability of winning this experiment is exactly 1/2. So the best possible adversary is just as good as the worst possible or dumbest adversary, the one we cannot hope to be secure against, right? Who just guesses what the message in a ciphertext was, right? And the probability is now taken over all random choices, meaning if the adversary is a randomized algorithm, this probability goes over the random coins of the adversary, plus the random choice of this bit B and the key generation. Okay, but let's make our 5-minute break and let's get back at 1:21. Let's continue. So there was a question that should be of interest for the entire audience. Your colleague asked, "Hey, what happens in the one-time pad, or let's say in definition 2 or 3, if M0 and M1 have different message lengths?" Right? Example, M0 is yes and M1 is no. What happens then? Okay, good. Go. Yes, please. That's already the 2 steps ahead. So the correct answer is when I defined the one-time pad, now I need to jump back a little. When I defined this, look here, the message space M is 0, 1 to the N. That means messages, ciphertext, and keys, they're all bit strings of length N. They can't be shorter or longer. In this message space, there are only messages of length N. And of course, if you want to encrypt shorter messages that are shorter than N bits, you have to come up with some mapping which takes these messages and maps them to N bit strings And of course, padding is filling the rest of the message up with zeros or blank spaces, if you want so, right? Encodes blank spaces as a zero or whatnot. That's one way to do this. Thanks for this question. And good, we're almost back. Yes, here we are. So, a natural question now is, so why does it give me 3 different definitions? Right? What's the point of this? I was perfectly happy with the first one, but then he tells me definition 2 and 3 generalize easier. Why do not start with definition 3, but then on the other hand, definition 3 looks only at a very specific attack, namely at a distinguishing attack, where the adversary chooses 2 messages and just wants to learn which one is encrypted in the ciphertext. Right? Maybe this is a weaker definition than definition 1, where our intuition about probability theory, namely message and ciphertext are independent, guarantees us that the ciphertext doesn't reveal anything about the message. Right? So why 3 definitions? Or what do we do now that we have 3 definitions? Should we just flip a coin and settle on one, or? Answer is they all say the same thing. If an encryption scheme meets definition 1, then it also meets definition 2 and 3, and vice versa, right? These definitions mathematically all say the same things, or they all state the same truth, so to speak. So they come in different gowns. They're dressed up differently to give us different interpretations. But at the core, they are all the same, right? And that's the next thing we're gonna look into now. And first, we're starting with definition 2 and show that it implies definition 1. So recall, what does definition 2 say? 2 says that, written in, let's say, mathematical short notation, for all pairs of messages M prime in M and all ciphertext C in C, it holds that probability enc K, M equals C is the same as probability enc K M prime equals C, right? Good. What does that mean? It means if we look, if we say, let's fix an M, and let's call this maybe delta of C comma M is probability that encryption K, right here, this probability just goes over K, and maybe some additional random coins used by enc of Km equals C. This is the same for all, is the same for all M, right? So once you fix a C, now no matter what M is, all these delta C are the same. So basically just the ciphertext, the ciphertext alone already defines the probability of occurrence independent of what message went in. All right, and now we want to show that this implies distribution definition 1, and therefore we're saying let M be any distribution of messages on or off? Off. You mean off? Or change. Let me guess. Change from green to a darker color. Yes. Sorry for. I mean, this is a little bit annoying that Microsoft PowerPoint is like really the only tool that allows me to put notes onto slides and keep them, while at the same time having animations and builds in the slides. A Keynote, I can make annotations in Keynote, but once I finish the talk, they're gone, right? You would see them on the video, but not on the slides that I put online. Okay, now let M be any distribution of messages. So what we want to show is that definition 1 holds, probability M equals M, given that enc K comma M equals C is just probability of M equals M, right? For all M and for all M comma C. I'm leaving their respective spaces away. So what are we gonna do? How are we gonna show this? How are we gonna, again, we're dealing with this conditional probability. How do we deal with conditional probabilities? Louder? Bass, good. So probability M equals M given enc K M equals C is via base the same as probability enc K M equals C given M equals M times probability M equals M divided by probability enc K M equals C. Okay, so this guy, I'm not gonna redo. I did that in the proof of perfect secrecy of the one-time pad. We know now that this is the same as probability enc K lowercase m equals C. Okay, so what's left to compute, and what's that probability? What do we call this? Enc Km. I introduced a shorthand for this. This one here. This is just delta C comma M. Okay, so what's left to compute, again, let's take a dark color, is this guy down here. And what's that? So this guy here, let's use blue. Probability enc Km equals C. What do we do here? This guy in the denominator, what do we typically do there? Law of total probability. So via law of total probability, again, we're going over overall, let's call them M star, because M prime I kind of used up there already. In M, probability that enc K comma capital M, now let's write it out, capital M equals C, given M equals M star times probability M equals M star. Let's move this guy up here for a minute. So What's this? This is the delta delta CM star, right? So here we have this sum overall M star, right? Probability M equals M star, but each of them multiplied by delta CM, but CM star, right? But now I said delta CM star doesn't really depend on M star, right? So delta CM star, this is the same as delta C comma, let's say 0 to the n, right? Let's go one further. Let's not use zero. Let's not use 0 to the n, but let's use our message m from up here. This is just delta cm. Okay, this is delta cm times this. And what's the sum overall probability m equals m star? What's that sum? That's just 1, right? So this expression in the end just becomes delta c comma m. So going back to the black thing here, this is just delta cm divided by delta cm times probability m equals m, and that's just probability m equals m, right? And we're done. That's what we wanted to show. Yes, please. Good. I said that here, let's use a color for that. This one here, right, uses that delta cm is the same for all m. So delta cm star is the same as delta c comma m. That is what that is the critical part in the security proof, because that's what what definition 2 gave us. Okay, definition 2 told us that this delta cm doesn't depend on m, only on c. For any pairs of m's, delta cm are the same, so delta cm is the same as delta cm star. So here, delta cm star is delta cm, right? This is what we're using here. All right? Is this clear? I mean, I see some further puzzled faces in here. So if we did a 5-minute quiz at the end of this lecture, who could reproduce this? Lift your arms, lower your arms. Who couldn't reproduce this? Ooh, okay, yeah, that's honest. Thank you. So this probably takes some time to digest, but again, what we said, this definition 2 said for any pairs of messages, these two probabilities are the same. And now I've just renamed them into delta CM, right? And now it doesn't matter if I call this pair of messages M and M prime or M and M star. Okay, good. So let's go on with our proof, best in black. Let's go from 3 to 2. Yeah. Okay, and this is also something that we're going to see a lot in this lecture. We're going to do this via contraposition. That means we assume we will show that not 2 implies not 3. right? If 2 is false, then if definition 2 is not met, then definition 3 will also not be met. And this is equivalent to if definition 3 is met, then definition 2 is met. Right? This is a very, let's say, the standard proof technique in complexity theory and cryptography that we do proofs by via contraposition. Good. Okay. So let's put the picture back up here. Assume 2 does not hold. Right? That means, i.e., there are messages, call them M and M prime, and a ciphertext C. This is a C, a very ugly C, such that, let's say, probability enc k m equals C not equal probability enc k m prime equals C, right? And if they're not equal, means one of them is bigger. And to make our life easy, we just assume without loss of generality, right? Green, you said, is bad. Without loss of generality, we assume that the first one is bigger than the second one. Okay? Good. And now our goal is construct an adversary A such that probability, well, int A equals 1 is greater than 1/2, right? Definition 3 required that this probability is always 1/2. And now I'm building an adversary which guesses this bit that we're hiding in this ciphertext with probability better than 1/2. Good. And what does my adversary do? Now, I really have to build such an adversary, right? And I mean, there's many options, but I'm gonna choose this one here. So here's the challenger. What kind of messages could my adversary A choose? Yes? There you go. M and M prime. So these guys, to highlight it with some color, are the same as those up there. Okay? So now the challenger does his thing and returns a ciphertext C star, right? A challenge ciphertext. What is my adversary speculating for? What is he hoping for to happen? Yes?
Like, that the long run of that, like if we...
No, they have the same length. The two messages.
I mean, we gamble that basically because they are equal, the one has a higher probability, and if we take the one with the higher probability, we don't have that.
But C prime is a fresh encryption, right? This thing here up here talks about a ciphertext C. There exists a ciphertext C, and now comes out a C star. Something completely different. You. What could my adversary speculate for? I mean, yes. I mean, you could always get for M prime. No. No. No, that's not what maybe you can build an adversary that that works in this setting, but my adversary, and this is mine, I'm building him, so I get to decide what he does, is he hopes that C equals C star, right? If C star equals C, what happens then? Let's say he's lucky and the challenger was dumb enough. I mean, he just does. He just follows his code, his procedure, and outputs whatever. Yes. He returns 1 exactly. Why? Then actually no. Then he doesn't return 1. My M0 is now M, right? And M1 is M prime. Exactly. Why? Precisely. So if the ciphertext happens to be C, if the C star happens to be C, then we know. Well, no. Ooh. Then we know by this here, right, that the message M is more likely to encrypt to C than M prime. Okay, so in that setting, it's a reasonable guess to set B prime equals 0. What do we do otherwise? If we're unlucky, yes? Exactly. So if we're unlucky not to disturb any probabilities, we just do the naive strategy of guessing a uniformly random bit, right? There we choose B prime uniformly from 0, 1. This is the naive strategy, so to speak. Right? And now we're gonna output our B prime. Okay, now I've given you an adversary. What I still wanna, 14 minutes left. Let's see how far we get. What I still wanna do is finish at least this part of the proof. So my adversary now distinguishes 2 cases, right? He does a case distinguishes cases. Let's call this case 1 and this case 2, right? So and I've said this quite a few times, what's the probabilistic or probability theoretic tool to analyze different cases? You definitely know it, but anyone else? Or what are we gonna use here to deal with these different cases? Yes. This literally asks for the law of total probability, right? But first off, I mean, there's some minor technicality. We need to show that probability C star equals C is greater 0. This is somewhat easy because really greater, not greater equals, but really greater, right? So we can apply we can actually do a decomposition of the space. Why is this the case? Because, well, probability C prime equals C is just, well, what is C prime? This is just a probability the same as enc k comma, let's say m equals c. We know that this is greater than probability enc k m prime equals c, and because this is a probability, it's greater equals 0. Okay, but now let's do our law of total probability stuff. We have that what we're interested in is the winning probability of the adversary, right? The probability that the experiment outputs 1. This is the same as probability experiment outputs 1 conditioned on C star equals C times probability C star equals C plus probability int A equals 1 given C star not equals C, probability C star not equals C. Okay. So what do we know about this? If C star is not equal C, what's the winning? Yes? Precisely. So in this case, we have this is exactly 1/2. Back. So what we're interested in now is this guy here. Okay. So what we want to show is probability int A equals 1, of course, equals 1 conditioned on C star equals C is greater than 1/2. We already have this feeling that this would hold. I mean, after all, this is how we constructed the adversary, right? But let's make the following observation. Under the condition, right? Under the condition that C star equals C, the events int A equals 1 and B equals 0 are equivalent. Why is that the case? So this is now sort of a kind of a leap, but why is this the case? So if we condition on the ciphertext being C star, why does this mean that the adversary only wins if the bit B, right, and the bit B is the one that's chosen uniformly here is 0. Yes. Precisely. So maybe slightly rephrasing it, in the case that we that we have the ciphertext, that the ciphertext C star is equal C, the adversary resorts to a deterministic strategy. He always guesses 0, right? So he cannot win if, in this case, he cannot win anymore if the encrypted bit is 1, okay? So if the ciphertext C star is equal C, the adversary will win if and only if the bit B was 0. Because then he defaults to say, okay, I'll put all my bets on 0, right? If the ciphertext C star occurs, then he will always bet on 0. Always on black, never never on white, right? Good. So this means that probability int a equals 1 given C star equals C is the same as probability B equals 0 given C star equals C. How do you compute this guy? How do you compute this? Probability B equals 0 given C star equals C. Now we got rid of all the, let's maybe fill in C star, right? This is the same as probability B equals 0 given enc KMB equals C. How do we compute this? It's a conditional probability. How do we typically compute conditional probabilities? With base. Exactly. So we have this thing, but I shouldn't lose track of time, is via base. It's the same as probability enc k comma mb equals C conditioned on B equals 0 times probability B equals 0 divided by probability C star or enc k m MB equals C. Okay. First, the easy things. What is probability B equals 0? That's 1/2. Good. Here, what is, I mean, this, what does this simplify to? Well, again, we can plug in B. So we have a probability enc k comma and m0 we know is just this m equals C. Okay, I think good. Let's quickly do this guy down here. Right? What is this? What is probability enc k comma mb equals C? What's that? How do we typically do this guy? Law of total probability. When we use base, the thing that comes up in the denominator, I mean, that seems to be a law of nature. Here we use the law of total probability. And this time we do it via the two events we're going to condition for are B equals 0 and B equals 1. Have 1 minute left. enc, say k m0, right? But m0 is m equals c times probability b equals 0. This is 1/2 plus probability enc k m prime equals c times probability b equals 1, but this is also 1/2. Okay. No, I'm not gonna be able to finish this in time. Then let's just pick up next time here and get finished with perfect secrecy in the next lecture. Thanks, everyone.